Hi. Hi, Leah.
Hi, Doctor.
Hello,
Hi, Doctor.
that's fine.
Hi, Mr. Ibrahim.
Ama je. Sana. Serius terus. Yes.
Okay. Assalamu alaikum, everyone. Good afternoon. So we're about to begin Catalysis Processes and Applications, Theory and Simulation of Nanosystems session. Please stand by. I would like to seek for your kind cooperation to avoid any virtual disturbance during the live broadcast session. If you have any question, the conference resource personnel are ready to attend you at the reception desk. Thank you for your kind cooperation and attention. We will start at 2 p.m., which is approximately about 5 minutes from now. Everything is okay, Leah? IT personnel? Okay. Assalamu alaikum wa rahmatullahi wa barakatuh. Very good afternoon, ladies and gentlemen. Welcome to the first Malaysia International Conference on Nanotechnology and Catalysis, MICNC 2021. We are now in the session Catalysis, Processes and Applications, Theory and Simulation of Nanosystems. My name is Lina Al-Ani, and I'm from NanoCat Research Center at UM. I'll be the session chair today, together with the session moderators, Ms. Leah Zaharani and Mr. Abu Hashim. I invite all the invited speakers and presenters to request to share audio and video now. Okay, ladies and gentlemen, just to announce, the oral presentations will be evaluated for the awards under two categories. The first category is for the best session presenter that will receive a certificate for best presenter, and I will announce it at the end of the session. While the best presenter award, that is offering a prize money from 500 to 1,000 ringgit, trophy and award certificate, it will be announced during the closing ceremony after this parallel session. I would like to seek your kind cooperation to mute your mic if you are not presenting and to avoid any kind of virtual disturbance as possible. For those who intend to ask questions to presenters, you can channel your question in the Q&A box. I will read it after every presentation. You can also request to share your audio and visual to ask your presentation in live mode. Presenters are given 15 minutes for presentation and 5 minutes for Q&A session, whereas invited speakers are given 25 minutes for presentation and 5 minutes Q&A. The IT personnel will help me to ring a bell sound as a reminder for the presenter around 5 minutes before the presentation time ends, and I will ask the presenter to wrap up his presentation when the time exceeds the 5 minutes allowed. Before we start this parallel session, I would appreciate if everybody can turn on the camera for a photo session. The IT personnel will take a photo. Okay. Thank you. Thank you very much. So without further delay, we will be hearing first a presentation from Mr. Jonathan. It's about characterizing metallic nanoparticle surfaces using unsupervised machine learning. The IT personnel will share a pre-recorded video, while Mr. Jonathan will join us later for the live Q&A.
Hello everyone, my name is John. I'm a PhD candidate from the Australian National University, currently working under the supervision of Professor Menabana. As you can see from the topic, the work I'm presenting here today is about the application of machine learning techniques to characterize the surface of metallic nanoparticles. Metallic nanoparticles have been regarded by some as the greatest catalysts of all time. This is because they exhibit the characteristics of both homogeneous and heterogeneous catalysts. For example, these nanoparticles are often highly catalytically active due to their high surface area to volume ratio, which is a typical property of homogeneous catalysts. At the same time, they could also be easily separated from their reaction mixtures due to their metallic nature, which in turn allows for recovery and reuse of the catalyst. Now we know that catalysis happens mainly on the surface of metallic nanoparticles, which is consisted of atoms with different characteristics. And each type of these surface atoms has been found to be associated with the catalysis of different reactions. For example, the amount of kinks and steps were found to be associated with oxygen reduction reactions, while proportion of terase atoms are correlated to catalytic activities in hydrogen evolution and oxidation reactions. So in theory, we could predict to some extent how well a nanoparticle is going to perform in catalyzing a particular reaction by simply knowing the concentration of each type of the surface characteristics. And this shows the importance of characterizing the surface features of metallic nanoparticles in order to design them as catalysts for specific reactions. This slide illustrates an attempt characterize the surface atoms of metallic nanoparticles computationally. Based on this labeling method, the surface atoms are grouped into categories with different ranges of coordination numbers, or simply the number of nearest neighbors of each atom. This is based on the observation that kinks, steps, corners, and edges always have the range of coordination numbers of 4 to 7, while the coordination number of terrace atoms roughly ranges from 8 to 11. Now this makes sense when we look at the ordered nanoparticles like this. But you might start to realize that the result could get quite arbitrary when it comes to more disordered nanoparticles. For example, we can see some flower-like patterns surrounding the yellow atoms visually, but couldn't really capture them with these labels. And of course, coordination number is by no means the only property that could be used to characterize the surface atoms usefully. In fact, we know that the catalytic activity of a nanoparticle can be influenced by a lot of other electronic and geometric factors, like how far are the neighbors of an atom from it on average, how symmetric are the neighbors around an atom, and what is the type of the elements. So the problem that we are trying to tackle here is there a way to design a new labeling scheme that incorporates the information from different atomic characteristics or properties? The good news is we could tackle this task using machine learning. In essence, machine learning is a study of algorithms that improve their performance in tasks as their experiences accumulate. Now, there are three types of machine learning problems, namely supervised, unsupervised, and reinforcement learning. So supervised learning aims to learn a mapping of relationships from inputs, or what we call features, to outputs, or labels. In reinforcement learning, an agent is trained to perform a task by trial and error interaction with its environment, while the goal of unsupervised learning is to extract the intrinsic patterns of the dataset, which is usually unlabeled, in the sense that the properties of interest are not provided to the algorithm. We chose to tackle this problem through an unsupervised learning task, namely cluster analysis. Note that the cluster here is different from the typical clusters that we talk about in material science. In cluster analysis, data samples that are similar are grouped together. The data are usually high in dimension, meaning that they're described by multiple numerical feature values. Now, there are many algorithms available for analysis, each with its own pros and cons. For this project, we have chosen the iterative label spreading method, which iteratively passes the label of initialized samples to its nearest unlabeled neighbors. Now, LS offers a few advantages over the alternatives. Apart from being used to conduct cluster analysis, it can also be used to evaluate the results obtained from other cluster analysis algorithms and optimize their hyperparameters. Plus, ILS itself has no hyperparameter that needs to be optimized. ILS has already been used to identify clusters in different materials, and so anyone interested are referred to these references. The raw data that we use here are structural data of palladium nanoparticles with different sizes, shapes, and ordering, which were generated from previous simulation works. Now, the data are provided in the XYZ file format, so it provides three types of information, which are the total number of atoms, the type of element, and spatial coordinates of each atom. Note that here, we treat each nanoparticle as a dataset, so each atom is a data sample. We call the process of turning raw data into numerical descriptors feature extraction. This is to prepare the data in a format that is more suitable for the machine learning algorithms to learn from. Feature extraction was performed on the raw data using multiple programs. One of them is called Network Characterization Package, or NCPack. It returns various geometric properties of any atom in a nanoparticle, like the statistics of bond length and angle, distance from center of a nanoparticle, the coordination number, and whether it lies on the surface. Here we color an icosahedron nanoparticle to illustrate the distribution of the extracted features across the nanoparticles. And we can see that some of these features provide information about the inner or bulk atoms as well. And these features are the foundation of the capability of our method, as we'll see soon. Apart from NCPack, more features were extracted using Python Structural Environment Calculator, which provides various parameters that describes the local atomic structure environment. And these parameters have all been used to identify crystal structures and distinguish between solid and liquid before. And those who are interested could refer to the references below for more details. Here we illustrate the feature distributions using the same nanoparticle cross-section. You might have realized that some of these features, for example the Steinhardt parameters, actually characterize the atoms to greater detail compared to the features extracted using NCPAC. So the inclusion of these features could actually provide greater diversity of information and helps to distinguish between the atomistic patterns. To further massage the data into a state that is ready for machine learning algorithms to learn from, we then process the extracted features in the following way. Now, it is common that some of these features are highly correlated with each other, and this causes redundancy if they are all included for cluster analysis. So remove one of each pair of these highly correlated features. The features that are controllable or easier to interpret have the priority to be retained. Next, the distribution of these features are normalized to the scale of 0 to 1. And this is especially important for clustering algorithms that require distance measures, including ILS, because if the values of the features are on the same scale, some of them will dominate over others during the distance calculation, and hence affect the results of the cluster analysis. Finally, the features that have constant values or do not vary too much are removed because they don't provide much information to distinguish between the atoms. For example, the bond lengths of the atoms in a perfect FCC cube are always the same. So in this case, we don't include the related features for cluster analysis. I will now briefly explain the output of the ILS algorithm. ILS returns minimum distance plots as shown here. Each of these points represents an atom of a nanoparticle. The Y value of each atom is its distance from the atom that it is most similar to in the feature space. So the points within two peaks are relatively more similar to each other. And whenever you see a peak, you should interpret the sample as being dissimilar from the previous sample. Now note that I've said feature space and not Cartesian coordinate space. So the atoms on the opposite sides of the nanoparticle could still appear very close together in the ILS distance plots. Here are the results of the ILS distance plots for nanoparticles with different shapes, which I colored by whether the atoms belong to the surface layer. Now looking at the ILS distance plots, we could see that it's possible to achieve satisfactory separation between bulk and surface atoms, as long as we could find the highest peaks in the middle. The only exception are decahedron and rhombic dodecahedron, where some bulk atoms are mixed within the surface atoms cluster. You might also have noticed the little peaks in between the bulk and surface atoms. They're indicating that there are subclusters within surface and bulk clusters. To find these clusters, we need to label an atom in each of them and rerun ILS. But to do that, we need to first identify these peaks. So if we were to analyze these ILS distance plots in bulk, an automated peak finding algorithm is necessary. So we devised an algorithm specifically to find the peaks in ILS distance plots. And here are the three criteria that a sample needs to satisfy in order to be identified as peak. Firstly, the peak has to be a unique maximum within a minimum size range of a cluster. Secondly, the signal-to-noise ratio of the peak has to exceed a threshold. And lastly, the peak also needs to exceed a threshold that ensures its visibility to human eye. These parameters could be tuned to vary the sensitivity of the algorithm, although we are currently setting it to mimic the decision of a human expert. We now look at the clusters identified using ILS and the peak finding algorithm. You can see that the algorithm works equally well across different shapes, and the resulting clusters make a lot of sense from the catalysis point of view. The clusters mostly correspond to the atomistic patterns that we are familiar with, like edges, corners, and different faces. It is also interesting to see that the method is capable of distinguishing bulk atoms, like twin planes and the subsurfaces. So this could actually be of interest to those who work with DFT calculations, which might be sensitive to the inclusion of subsurfaces, and those who wish to characterize inner atoms of materials like high entropy alloys. Now, it is possible that not all of these features are necessary for good classroom results. Unfortunately, unlike supervised learning, we don't have a straightforward way to further refine the features to be used for unsupervised cluster analysis. So to simplify the system and to speed it up, a game theoretic approach is being taken to measure the effect of each group of features on the clustering results. We first group all the features into 6 categories and generate their combinations. The cluster analysis is then carried out using each of these feature combinations. And here we show the LS distance plots from 3 different combinations of features, which had identified different clusters. So naturally, the next step is to evaluate these clustering results. Now, we attempted to evaluate the clustering results both quantitatively and qualitatively. 3 measures are available for quantitative evaluation of the results when ground truth labels are unavailable. Unfortunately, we don't have time for detailed explanation of these measures. For those interested, could refer to the references here for more information. But one thing to note is that a good value of these measures doesn't necessarily mean that the clustering results are optimal. We still have to back this up with our domain knowledge. And this is where the qualitative evaluation comes in. The clusters found from the LS distance plots are compared to what we would expect if a catalysis expert was asked to group the atoms. The combinations that return more similar results will be given a better ranking score. And this will eventually help us to identify an optimal list of features for general use regardless of the nanoparticle shape. In conclusion, we showed that LS clustering has great potentials in the characterization of surface patterns of metallic nanoparticles. The LS plots also allow one to achieve good separation between bulk and surface atoms without having to visualize them. The method should be easily transferable, so it could be useful to researchers studying various other nanomaterials. Since the cluster analysis results are subjected to the identification of peaks in the distance plots, in the future, we would like to develop better peak finding algorithms that are higher in specificity and sensitivity. Once the optimal feature combination is identified from the game theoretic approach, we will also check the potential of using it as a new surface labeling method for nanoparticles, for metallic nanoparticles as catalysts. The limitation of the results so far is that these are only applicable to perfectly ordered nanoparticles. So we will definitely extend test cases to disordered nanoparticles to generalize this method. And that is all from me. Thank you for your attention.
Thank you very much, Mr. Jonathan. That was a great lecture here. And I'm very interested to know that you are using also Python, because this is like the trend currently, not only in the research, but also in many industry. So let's look at the Q&A. You have 2 questions. The first one is, thanks, Mr. Jonathan. May I know if it's possible to use machine learning to predict optimization and optimum condition for metallic nanoparticles synthesis?
Yeah, thanks for the question. Absolutely, actually. If you have attended the plenary talk, the 3rd plenary talk actually on Wednesday, which is given by my supervisor. So she's been giving multiple examples, I suppose, of such application of machine learning. So it's actually very, very common among the field of applied machine learning to do this prediction of certain properties. So in this case, you want to predict the optimum conditions for the synthesis of a particular metallic nanoparticles with certain set of functions, right? So on Wednesday, she presented that you could kind of reverse what we do usually. So usually what we do is we let the machine learn the relationship between the independent variables and the dependent variables that you provided to it. And then when you give it unseen examples, so say you want to predict the properties of metallic nanoparticles with a certain set of independent variables, you'll be able to predict it, and you can use the output of the prediction for something. But in this case over here, you want to do the opposite. So you want the machine to learn the I guess the settings that you want to use to synthesize the metallic nanoparticles with the set of independent properties, independent variables that we can control in the lab. So it's totally doable as long as you could gather a nice spreadsheet of these required information. These machines can actually do a lot of incredible things.
Okay, that's great. It will save a lot of time and energy in the lab by doing that. Yeah. So the second question is great sharing. Are you using Python to build up a template script that you can apply to different types of metallic nanoparticle, or is it a case by case?
Right. I suppose by case, you meant that I did the same thing over and over again for nanoparticles with different shapes. That's certainly not the case. I suppose when we are doing computational sciences, we always aim to generalize our scripts, our programs as much as possible. So in this case, yes, I have data, so metallic nanoparticles of different shapes, but my program is relatively short, I suppose. So what I have is a rather generalized script that could apply to any data with XYZ format, basically. So it's not really limited to metallic nanoparticles. As long as you have any data set at all with in the XYZ format, like even the biomolecular data set, it's also applicable. But yeah, in this case, we are only applying it to palladium metallic nanoparticles. Yeah.
Thank you. Thank you very much. We have also another question. Interesting topic. Thank you. What is the novelty of this work when it is compared to other similar works?
Right. I guess the greatest point to take away from this presentation is that traditionally we have always, like even in the related machine learning applications, we've always been describing or characterizing the surface of a metallic nanoparticle with only one property. So in the previous work of my supervisor, which is most closely related to this work, they're using surface coordination number, so number of neighbors of each atoms on the surface to describe the atoms on these metallic nanoparticles. Now this scheme could be useful in some case, but as I presented earlier, as I pointed out earlier, it can't really capture a lot of patterns that we can see visually. So hopefully using this method that we have just developed, we can combine the information from different atomic properties that you are interested in. So not only the coordination number, maybe even the bond length statistics, the angle statistics, a lot of other electronic or geometric features. If you could gather them, as long as you could find them, you can combine them together in some way. So hopefully the labeling scheme that we come up with will be useful in the later work. So this is very much early in the stage, I guess.
Okay, great. Thank you. Thank you, Mr. Jonathan, very much for your nice presentation. Very interesting indeed. Thank you.
Thank you.
Okay, so moving along to our next presenter, please welcome Mr. Ibrahim Abdullah for his speech on thermodynamic study of methane and water adsorption on iridium, palladium, platinum, and nickel surfaces. Also, the IT team will help to share the pre-recorded video, as I learned from them, while Mr. Ibrahim will join us later for a Q&A session. Okay, please, Leah. Okay, thank you.
Good day, ladies and gentlemen. My name is Ibrahim Abdullah. I'm here to present the paper on thermodynamic study of methane and water adsorption on iridium, palladium, platinum, and nickel surfaces. This is the presentation outline. Introduction. What is catalysis? Catalysis is the acceleration of a slowly proceeding chemical reaction through the presence of a foreign substance. For a simple reaction A and B to give C, A and B have to meet each other. The collision theory depends on the concentration of A and B. It turns out that not all collision theory lead to reaction to form a product. First, the reactant has to climb the energy barrier. The rate constant is proportional to the exponential of the activation energy divided by RT. What the catalyst does is to offer an easier path with lower energy barrier, thus higher reaction probability. We have two types of catalysis. We have the homogeneous catalysis, that in which the catalyst has the same phase as the reactant and product. They usually have high selectivity, but the catalyst recyclability and product separation poses a serious challenge. Whereas the heterogeneous catalyst is that in which the phase of the catalyst differ from that of the reactant and product. The catalysts usually are in solid phase, whereas the reactant are usually in gaseous or liquid phase. There are different time and length scale in heterogeneous catalysis. When we talk about reaction, we can see directly the reactor having reactant entering the reactor and product leaving the reactor. When we zoom into the reactor, we can see there are a lot of pellets in the reactor. When we further zoom in, we see there are a lot of react catalysts located on the pellets. In the atomic view, we see that there's reaction happening on the surface of the catalyst. The microscopic transformation can always be broken down into elementary steps. First, the catalyst have to bring the reactant to the surface to form an adsorbate. The adsorbate will then diffuse to the active site, break down the chemical bond and form new bonds. Finally, the product will dissolve from the surface to regenerate the active site. From this, the catalyst performance is controlled by the elementary step. Reaction kinetics can be determined using first principle. First principle calculation on heterogeneous catalysts are mainly based on density functional theory calculation. Density functional theory calculation method employs the optimization of three-dimensional electron density to solve the electronic Schrödinger equation. And we have mainly three approaches. We have the cluster approach, which presents the surface by a finite number of atoms. This type of model is the most basic and computationally the fastest. Its accuracy, however, is variable depending on the size of the catalyst. It is generally inadequate to model any kind of extended metal. Next, we have is the embedded cluster approach. And this method improves on the cluster approach by introducing electrostatic constraint on the cluster imposed by the environment. Then the third we have is the periodic slab model. This model mimics infinite extended surface and is the only approach that reliably captures the dislocalized metal bonding. It is the best practice for metal surface calculation, but requires large computational cost. The methane steam reforming process is used for the production of hydrogen and syngas from methane and water. The main challenges of methane steam reforming are sintering, which is the induced loss of catalyst surface area, and coke formation by the deposit of carbon on the surface of the catalyst. Yet our 2013 did work titled Densitochronology Study of Methane Dissociation and Platinum, Iridium and Platinum Iridium Surface. CH4, CH3 and hydrogen preferred absorption on the atom site on the iridium 111 surface. Rodriguez et al. 2014 did work titled Thermodynamic Study of Benzene and Hydrogen Co-absorption on palladium 111 surface. The inclusion of vibrational contribution to the surface give free energy are recommended to predict the thermodynamically most stable surface coverage. Louis et al. 2015 work titled Coverage-Dependent Water Dissociative Adsorption of on Iron 110 from BFT computation. Water preferred absorption on the atom site on the iron surface. Both absorption and hydrogen bonding plays the role in the stabilization of the water cluster on the surface. How et al. 2018 drug title Density Functional Theory Study on Coverage-Dependent Absorption Dissociation Aggregation of Water on Clean and Pre-Adsorbed Oxygen. The water desorption is more favored than its dissociation on the clean copper surface at different coverage due to the weak physical interaction between the water molecule and copper surface. The aim of this research is the thermodynamic study of methane and water adsorption on iridium, palladium, platinum, and nickel 111 surface using the supercritical theory calculation. And the aim of this work can be achieved through the following objectives: to investigate the dependent absorption and dissociation of methane on clean nickel, iridium, palladium, and platinum surface at different coverage using the supercritical theory based calculation; to investigate the dependent absorption and aggregation of water on clean nickel, iridium, palladium, and platinum surface at different coverage using best structural theory calculation to determine the surface give free energy for methane and water absorption on nickel, iridium, palladium, and nickel surface at different coverage. Methodology: we initialize the system by developing a SLAB model on the metal surface, after which it will optimize it will determine the absorption energy of methane and water at different coverage and evaluate the surface give free energy of the methane and water absorption on the different metal surface at different coverage. The coverage effect was determined by, for the methane, a single methane molecule on a 3x3, 2x2, 2x1, and 1x1 unit cell to replicates different coverage of 0.1, 0.25, 0.5, and 1.0 monolayer for the water molecule by increasing number of molecules in a fixed unit cell, 2x2 unit cell from 1 to 4. This figure shows the top and side view of a clean metal surface, in which we have different sides such as the top site, the bridge, the HCP and FCC. And this here we have the 3x3 unit cell, 2x2 unit cell, 2x1 unit cell, and 1x1 unit cell. And we have 4 layers. This figure shows the schematic representation of determining the activation energy, in which we generate the set of elementary reaction steps, then optimize and calculate the initial state energy. Here we have the methane absorbed on the surface, and optimize and calculate the final state energy. Then we have the CH3 plus hydrogen. Now we search and calculate the transition state using LST QST method, in which you have the transition state. After that, we will calculate the activation energy. Surface gives free energy is used as a standard to test the stability of water and methane absorbed system under different conditions. It is determined using this equation 2, and the more negative the surface free gives energy, the more stable the absorbed structure. This table shows the absorption energy of methane absorbed at different sites on the metal surface at different coverage. The first absorption site for methane is the atomic site for all the metal surfaces, which are related works. At coverage of 0.5 and 1 monolayer on the metal surface, the absorption energy was positive, showing that the absorption process was thermodynamically unstable. For methane absorption on palladium 101, the most stable absorption site was the atom site with absorption energy of minus 13.6, which is in close agreement to the experimental value of 17.02. From this table, methane have the strongest interaction with the palladium 101 surface. The methane interaction with the metal surface is very weak, which indicates physical absorption. This figure shows energy profile of dissociation from CH4 to CH2 on the metal 101 surface. The methane dissociation is preferred on the iridium surface than on the other metal surfaces. This table shows the water absorption on the metal surface at different coverage. Water absorption on the nickel 101 surface, which favors absorption at the atom site, having absorption energy of minus 44.76 and minus 42.23 at coverage of 0.11 and 0.25, which agrees with the experimental value of minus 42.45. So it was observed that the water molecule has the strongest interaction with the iridium 101 surface. This figure shows the most stable absorption configuration of water aggregation at different coverage on the palladium 101 surface. This table shows the formation energy, absorption energy, and hydrogen bond interaction energy for water on the different metal surfaces. And the results show that as the number of aggregate water molecule increases, the stronger the hydrogen bond interaction between the water molecules, and the weaker the interaction of the water and the metal surface. And so it was observed that iridium had the strongest interaction with the water molecules, whereas nickel had the weakest interaction. This figure shows the surface gift-free energy as a function of temperature at pressure of 1 bar for the methane absorption on the clean metal surface. And observe that at coverage of 0.5 and 1.0, the source gift energy is positive, and at coverage of 0.25 and 0.11, the gift energy is negative. And the more negative this gives you energy, the more stable the absorbed structure. And you can observe that platinum has the most stable structure, followed by platinum, followed by iridium, followed by nickel. This figure shows the gift-free energy as a function of temperature for water absorption and the clay metal surface. The palladium 101 surface was the most stable coverage for the metal and water absorption at all the absorbed coverages, followed by the palladium surface, followed by iridium surface, followed by the nickel surface. Conclusion. The following conclusion can be drawn from the research. For methane absorption in the metal surface, the favorite absorption site is the atom. At coverage of 0.5 and 1.0 monolayer, the absorption of methane on the metal surface was thermodynamically unstable. From water aggregation on the metal surface, the increase in the number of water molecules increases the interaction of hydrogen bond with the water molecules and weakens the interaction between the metal surface and the water molecule. The thermodynamic stability of methane and water on the different surfaces are ranked in decreasing order. Platinum 101 to palladium to iridium to nickel. Yes, of my references.
Thank you. Thank you very much for the interesting presentation by Mr. Ibrahim. So now we come to the Q&A session. Thanks, Mr. Ibrahim. Have you investigated the effect of the exclusion of varying layers of subsurfaces of the metal slabs? If so, may I know how significant are the differences of the results?
Please come again. I didn't get the question.
No problem. I will repeat. Thank you, Mr. Ibrahim. Have you investigated the effect of exclusion of varying layers of subsurfaces of the metal slabs? If so, may I know how significant are the differences in the results?
Okay. Thank you for the question. From previous works, the recommended layer is usually 4. Therefore, I took that as a standard for this work. The minimum of 4 layers is normally used to replicate a surface. Therefore, I use just only 4 throughout the whole work.
Okay, thank you. Thank you, Mr. Ibrahim. We have another question also. Nice presentation, Mr. Ibrahim. Can you please explain further about sintering as a challenge for nickel formation?
Okay. For nickel formation, sintering was not okay. For sintering means that you have more than one metal on the surface and another metal. For this particular work, it was not considered, but yes, you can actually determine the effect of sintering using density functional theory.
Okay, thank you. Thank you, Mr. Ibrahim. Another question. Hi, Mr. Ibrahim. It was tricky to find the transition state structures of 2 organic molecules. Is it easier in an inorganic system like this?
Please come again.
The question says it was tricky to find the transition state structures of 2 organic molecules. Is it easier in an inorganic system like this?
Usually it's not easy to find. It depends because the idea for to find the transition state, you have one imaginary frequency. If you have more than one, means that you have not found the transition state. Therefore, you must have one imaginary frequency. I think that's the standard that have been used. Therefore, that frequency will determine the turnover frequency from the reactant to product. Therefore, there are different. Like for this work, we used the mole package, the mole model in Material Studio, and that in the Material Studio actually has platforms to actually segregate or differentiate the imaginary frequency from others. Therefore, if you calculate it and you're able to get one, means that you have found the transition state. When you have more than one, means you have to search again to find that particular transition state, ensuring that you only have one frequency. But for surfaces, it's a bit easier as compared to just organic molecules reacting themselves.
Thank you, Mr. Ibrahim. We have also another question. Were other types of surfaces like 100 and 110 investigated as well?
For this work, no. We only investigated for the 111 surface.
Okay. Okay, and another question. If platinum is the most stable, can we consider that at different metal surfaces of platinum, it will also give the same stability?
Yes, I considered 4 different coverages. And from the 4, I considered platinum gave the most stable, thermodynamically most stable for the absorbing, that's for the methane and water absorption. Therefore, we consider 4 different coverages. But from the work, we observed that very high coverage of 1 and 0.5. The coverage were positive, meaning that it is not stable on that surface. Therefore, when we have it lower than 0.5, they became negative, which will make it stable on that surface.
Okay, thank you. Thank you very much. I guess we don't have any more questions. Thank you, Mr. Ibrahim.
Welcome.
Thanks. So now we are moving along to our third speaker. Please welcome Mr. Surya for his presentation on evaluating the performance of bismuth ferrite incorporated regenerated cellulose nanocomposite as a potential photocatalyst. The stage is yours, Mr. Surya.
Good afternoon, all of you. I hope you can see my screen.
Yes, we can.
So my research title is Evaluating the Performance of Bismuth Ferrite Incorporated Regenerated Cellulose Nanocomposites as a Potential Photocatalyst. I am PRD Veerasuri. This is presentation outline. Let's see what are the highly prevailing global issues. As we know, COVID-19 pandemic is the major. Secondly, air pollution, land pollution, water pollution, depletion of renewable energy sources, and altogether economical crises are dominant. Out of them, wastewater is a highly prevailing environmental concern because several organic matter is contaminated with incoming wastewater from industries. Industries utilize several dyes according to their application requirement. These dyes are organic matter and harmful to humans as well as other live species. Methylene blue, methyl orange, and some other dyes are popular. The available conventional treatment methods can be categorized into three major types as biological, chemical, and physical. Whatever the method, there is a major disadvantage associated with these three types, that is formation of secondary sludge. It is another environmental burden which should be additionally treated. Therefore, photocatalytic degradation is a highly demanded process as an eco-friendly water purification process. This method has no secondary sludge. The system consists of photocatalyst, light, and light energy. What is a photocatalyst? It is a substance which utilizes light energy and performs redox reactions to accomplish the degradation mechanism. In general, to have a successful degradation process, less band gap energy is preferred, which is less than 3 electron volt. Semiconductors were identified as suitable materials to use as photocatalysts. However, the conventional semiconductors have a wide band gap energy which is greater than 3 electron volt. In this scenario, bismuth-based compounds were identified as potential materials to use as photocatalysts. Therefore, in this research, bismuth ferrite was selected as the photocatalyst. It has an energy gap in the range of 2.2 to 2.7 electron volt. Bismuth ferrite can be synthesized as a powder in laboratory scale, but when we are going to reuse these powder type materials, we have several disadvantages like difficult separation, high cost, time consumption for recollection, as well as agglomeration at high loading. Therefore, immobilization of these powder type materials into a fixed geometry is a mandatory requirement. Hence, biopolymers were identified as suitable immobilizers to incorporate these powder form materials to eliminate the formation disadvantages. In this research, oil palm empty fruit bunch based regenerative cellulose was selected as the biopolymer to incorporate the selected bismuth ferrite powder, and this research aimed to synthesize regenerative cellulose bismuth ferrite nanocomposite film as the photocatalyst to evaluate the degradation of dyes. Above mentioned problems can be summarized in this way. Wastewater is a highly prevailing environmental issue because of organic pollutants. On the other hand, depletion of non-renewable resources and accumulation of synthetic waste are another environmental problems, and altogether they bring environmental impacts. And to defeat these environmental impacts, from one end there is a huge demand on renewable resources, that is utilization of biopolymers. From another end, there is a huge demand on eco-friendly neutralization techniques, that is photocatalytic degradation, to overcome the secondary starch accumulation. In this research, oil palm empty fruit bunch was selected as the source to synthesize microcrystalline cellulose And after obtaining microcrystalline cellulose, it was mixed with prepared bismuth ferrite using ionic liquid to obtain the photocatalytic film. As the dye to evaluate the degradation mechanism, methyl orange was selected as the adsorbate. So the research objectives are to determine the best bismuth ferrite composition in RC matrix and the best process conditions to obtain a maximum degradation of methyl orange. Secondly, to determine the reusability of these photocatalysts used in the identified base condition. MCC was microcrystalline cellulose. MCC was synthesized starting from OPFB using the methodology explained by the scientist Batista. This is the microstructure obtained for MCC particles, and the particle size distribution was shown here. Bismuth ferrite was synthesized starting from bismuth nitrate and iron nitrate with the aid of biotemplating method. This is the morphology obtained from bismuth ferrite particles, and particle size distribution was shown here. According to particle size distribution, particle size is less than 100 nanometers, and therefore the film we are going to synthesize from these bismuth ferrite particles is a nanocomposite. This is the activity flow in the research. Initially, photocatalyst preparation and simultaneously characterization and color removal experiments were done. After that, optimization of bismuth ferrite content and pH of dissolution, and secondly, reusability study was conducted and conclusion was derived. The photocatalytic film preparation involves dissolution of MCC with bismuth ferrite using ionic liquid BMIMCl at 80 degrees Celsius. In this dissolution, bismuth ferrite content was varied as 1 to 5% by weight with respect to MCC weight. After obtaining a homogeneous melt, the melt was subjected for solution casting to obtain a film, and the film was coagulated inside distilled water for 24 hours and conditioned to obtain a dry photocatalytic film. In the characterization, this is the FTIR spectrum obtained for bismuth ferrite powder and prepared photocatalytic films. The right side figure shows the FTIR spectrum obtained for PORC and photocatalytic film. The black curve represents the FTIR spectrum obtained for PORC, and red curve represents the FTIR spectrum obtained for RC bismuth ferrite composite. So according to that, the FTIR's two spectrums are similar, and therefore it can be confirmed that the incorporation of bismuth ferrite does not interfere with the chemical structure of PORC. According to morphology, the left side figure is the morphology of PORC, and the right side figure is the morphology of photocatalytic film. The white spots are bismuth ferrite particles, and this confirms successful physical blending. After making the photocatalyst, the ethyl orange dye was prepared with 4 different concentration: 10, 15, 20, 25 ppm with 5 different pH values: 2, 4, 6, 8 and 10. After that, the prepared photocatalyst was immersed inside dye, and initially dark treatment was conducted for 1 hour to achieve the adsorption-desorption equilibrium, and after that irradiation was allowed. The irradiation experiment was conducted from 10 am to 3:30 pm time as the maximum irradiation time. During the experiment, every 30 minutes, 5 ml of the dye was taken out and subjected for UV visible spectroscopy analysis after centrifuging at 4000 rpm for 10 minutes. And in UV visible spectroscopy analysis, absorbance versus wavelength graph was obtained, and the maximum absorbance observed at 465 nanometers. This absorbance value was used to calculate the concentration of dye at each interval with the aid of Beer-Lambert law. After calculating the concentration, color removal efficiency was calculated using this equation. These three figures shows the maximum color removal efficiency variation with pH value, bismuth ferrite content, and concentration of methyl orange. According to that, the average highest color removal efficiency was obtained as 90.4%. That was obtained at pH 2, 10 ppm, and 3% of bismuth ferrite loading. So according to the observation, at pH 2, the degradation is highest. That is, when the H plus concentration is higher, the catalyst surface is positively charged. Methyl orange is an anionic dye, and anionic dyes are preferred to attach with the positively charged surfaces, and therefore absorption is increased, and degradation is improved. At high concentration, the sunlight absorption is difficult and therefore degradation is reduced. When the catalyst dosage is increased at excess catalyst dosage as a result of agglomeration, the ability to reach the adsorbate into active site of the catalyst is weakened and therefore degradation is reduced. Also, agglomerators catalysts undergo self-light scattering within the on particle and therefore degradation is reduced. Further, agglomerated catalysts reduce the turbidity of the dye solution, and that also restrict the light absorption and degradation is decreased. Now we have identified the best process conditions to obtain a maximum degradation. Those conditions are 3% of bismuth ferrite, 10 ppm of methyl orange, and pH 2. So the reusability study was conducted using these best conditions. After the first experiment, the catalyst was washed with distilled water at 200 rpm for 2 hours and dried overnight before the second experiment. This catalyst washing and reusing the degradation experiment was repeated until 5 cycles. So the graph shows the color removal efficiency variation with number of cycles at each repeated cycle. So it can be observed that color removal efficiency is reduced with number of cycles, and according to the images, it can be observed that the catalyst has become fragile at the end of fourth cycle, and that is the reason for the observed significant reduction of color removal efficiency at the end of fifth cycle. This might be due to the leaching of bismuth ferrite from RC film during breakage of the catalyst when it is subjected for continuous magnetic stirring. So then the conclusion can be derived in this way. The identified best bismuth ferrite content is 3% with respect to MCC weight to accomplish an efficient color removal, and the maximum degradation is 90%. That was obtained with 10 ppm of methyl orange and 3% of bismuth ferrite loading at pH 2. So the catalytic performance was stable for 4 cycles. So this is a suggestion. Actually, as we observed at the end of fourth cycle in the cyclic experiment, the catalyst is fragile. That is because of the less tensile strength of the film, which is around 10 megapascal. This is a suggestion. In the future research, it can be taken into account to enhance the tensile strength of the film by incorporating reinforcing fillets such as MMT with the purpose of improving the stability of the film for using for more number of cycles. And thank you.
Thank you very much, Mr. Wan, for the wonderful sharing on photocatalysis, such interesting field currently. So let's look at the questions. So the first question is, thank you for sharing your insightful work. What is the purpose of adding IL during the preparation of your film? Can you explain this in terms of chemical changes?
Can you repeat the question?
Okay. So the question was, what is the purpose of adding IL during the preparation of your film? Can you explain this in terms of...
Ionic liquid. You mean ionic liquid? It
Yes.
is to obtain the dissolved melt, because we use microcrystalline cellulose. It cannot be dissolved. This is cellulose. It is insoluble in water, and there are only limited solvents are available for dissolution. That is why we have used BMM-seal ionic liquid.
Thank you. Thank you very much. So the second question is, thank you, Mr. Wan. The optimization studies that you have performed investigated the effect of pH only, other parameters?
Three parameters: bismuth ferrite loading, pH, and concentration of dye.
Okay, thank you. Thank you very much for the explanation, Mr. Wan. Thanks. Okay, so now I would like to thank all our presenters. Now we have reached to our invited speakers. I'm pleased to welcome Dr. Lee Kiam Moon for his presentation on statistical modeling optimization approach for photocatalytic degradation of organic pollutants using zinc oxide-based photocatalysis. Doctor, the stage is yours.
All right, thank you. Hold on, I share my screen. All right, can you see my screen?
Yes, we can.
Can you see my slide moving?
Yes.
All right, very good. All right, thank you, Chairperson, for the kind introductions. Salam sejahtera and a very good afternoon to all of you. I hope now it's 3 o'clock. I hope you guys are still awake. Right, today I would like to share with you my research experience on a topic entitled a statistical modeling optimization approach for photocatalytic degradations of organic pollutants using zinc oxide-based photocatalysts. I'm Maurice, currently working as a senior research officer at Nanotechnology and Catalysis Research Center, Nanocat, University, Malaysia. So this is my presentation outline for my sharing section today. I will begin with some brief introductions on the research background, followed by zinc oxide photocatalysis. Then I will move on to the design of experiments and share a few studies on photocatalytic oxidations of organic contaminants. And finally, I will end my sharing sections with a brief conclusions. Generally, over 2/3 of Earth's surface is covered by water, and less than 1/3 is taken up by land. So the demand for the fresh water is constantly increasing. This is due to the population growth and overexploitations. According to United Nations World Water Development Report, the use of water has increased 6-fold over the past century and is rising by about 1% a year. According to Sustainable Development Goal 6, or known as SDG 6, which is part of the 2030 Agenda for Sustainable Development, stated that the access to safe drinking water and sanitation must be guaranteed for all within 10 years. So SDG 6 is one of the 17 SDG goals established by the United Nations General Assembly. So what does the report tell us? The report said that 2.2 billion people currently do not have access to the safely managed drinking water, and 4.2 billion of people or 55% of the world populations are without safely managed sanitations. The report also recalls 4 essential actions: the reductions of source pollutions, the treatments of contaminants, the reuse of the treated water, and the recovery of the byproducts. So in recent years, the water contaminations issue in both ground and surface water attracts more and more attentions. So some common organic contaminants that harm our environments are agriculture runoff, industry effluents, herbicides, insecticides, pesticides, heavy metals, oil spillage, pharmaceuticals, textile dyes, toxic chemicals, and so on. So, what is the effect of the water pollutions? The most impact is the human health, because humans easily get sick due to drinking water is unsafe. The water quality is dropped due to we have very limited clean water for our daily life usage. Of course, the biodiversity, particularly forests and wetlands, are also under threat. The aquatic ecosystem becomes imbalanced due to the reductions in the numbers of aquatic animals or plants. And finally, there is an increase in the financial burdens on the governments who need to spend millions and millions in order to restore the water bodies to its natural state. So, what can be done? Even though many conventional treatment methods are widely used, they are still unable to remove entirely the recalcitrant organic molecules. The physical methods such as adsorptions, flocculations, membrane filtrations, reverse osmosis are not very efficient and only degrades the pollutants to other media, thus causing secondary pollutions. So some methods, although they enhance the efficiency of the photodegradation rates, however, they are limited by the high operating costs and expensive materials. So what we have now, advanced oxidation processes, or known as the AOPS, has been studied extensively and serve as a promising technology to deal with the environmental issues. So this is due to AOPs is efficient and cost effective, and it has a strong capabilities to mineralize a wide range of recalcitrant contaminants. Photocatalytic oxidations were recommended strongly as low-cost methods of high removal efficiency compared with the others AOPs. So in a photocatalysis principles, the light energy equal to or higher than the band gap energy of a semiconductor generates electron hole pairs on the photocatalyst surface. So the photogenerated hole can oxidize water or hydroxyl ions of the aquatic environment to hydroxyl radicals. And the electrons will be absorbed by the oxygens to generate superoxide radical ions. So these radicals can react with the pollutant molecules and mineralize them into the CO2, carbon dioxide, and water. So zinc oxide photocatalysis. These are some of the characteristics of the zinc oxide. So it has a band gap energy around 3.37 electron volts, non-toxicity in nature, highly abundant, relatively low cost, and superior catalytic activities. So due to its excellent photocatalytic activities, zinc oxide has been widely adopted as the photocatalyst in removing various types of organic contaminants, such as dyes, herbicides, insecticides, and pesticides, pharmaceuticals and personal care products, PPCPs, phenolics, heavy metals, endocrine disrupting chemicals, EDCs, and so on. So these are the factors who affect the photocatalytic degradation efficiency. For example, catalyst loading, initial concentration, the solution pH, the light intensity, the irradiation time, and inorganic species. So their management and handling seems complicated and confused because now you need to deal with such a large number of the parameters. So if these experiments are carried out without a rigorous methodology, they will lead to inconsistent results. So that's why the design experiments come in. So until today, this is still a need to acquire experiment design. So in order to minimize number of experiments and to maximize the yield from both technological and methodological points of view. So with response surface methodologies, or RSM in short, is a combination of statistical and mathematical methods for optimization studies in a complicated process. So, as I mentioned before, most of the photocatalytic studies are conducted by a conventional way known as one factor at a time. This means it only changes one parameters while other parameters are kept constant. So the OFAT method has common shortcomings. Interactive effects amongst the study variables or parameters are not included. So inethical optimizations towards the response, time wasting as more experiments are needed to be conducted, and costly because you need more reagents and materials. So the advantages of RSM are RSM considering the interactive effects between the study parameters. So RSM also able to determine the combinations of levels in order to optimize the process more accurately. Of course, it only requires small number of experiments with many data. And lastly, cost saving. All right. So due to its advantages, RSM has been commonly used in the experimental design of the photocatalytic treatments of various types of organic contaminants. As you can see here, the target can range from the methyl orange until the ibuprofen, or some study carried out on the catechol bisphenol A and phenoxyacetic acid. So these are some of the general terms that normally apply in RSM study. Of course, there are many terms if you're referring to the book, all right? So these two I picked out for you to understand what I'm going to present later on. So the first one will be factors or independent variables. So what are the factors or independent variables? So they are the experimental variables that can be changed independently. So commonly, this is your process parameters, okay? So responses or dependence variables. So these are the measure values of the experimental results. So here come to these second order polynomial model equations. So since it is mandatory to introduce the interactive effects of the process parameters, polynomial regression models is normally applied. So the positive sign in the regression equations represents the synergistic effects between the parameters, while the negative signs indicates an antagonistic effects. So the optimal values of the parameters or the efficacy of the models were obtained through the estimations of the regression equations and the interpretations of the response of the contour plots. So I believe before you start a typical experiment, screening test is the most important one. All right. So we're looking to optimize photocatalytic reactions, center composite design. ISM require studying 5 different levels of parameters codings. So from negative alpha, -1, 0, +1 to positive alpha. All right. So the factors that could be applied here are the catalyst dosage, the initial concentrations, the pH, the irradiation time, and light intensity, and so on. All right. So this is an example, okay, from my previous study. Once you put in all your factors, you will get and range, you will get a table like this. All right. So after you have fixed your factors, or your process parameters in short, so you need to select a response. So the possible response could be the degradation percentage, so the decolorization rate, the degree of mineralization, and so on. So once you have decided your factors, you have decided your response. So what you're going to do? So the software will generate a series of experimental runs. Okay, starting from 1, 2, 3 until 20 or 30 and even more. So then what should you do? You just need to perform the experiments by referring to the experimental conditions and key in the data accordingly. Let me show you an example here. So once you have key in your determine your factors, right? You key in your range, okay? So then the software will generate, for this example, 20 runs, and later you key in what you get from your experimental works and compare with the predicted values from the response. All right. So now I'm going to share with you some of my previous studies. Okay, so first, the analysis of variance or ANOVA. Okay, so this table shows the ANOVA for the response surface of a quadratic models. So what we can see here is from the ANOVA, the model is significant because of the model has a highly significant p-value. So the lack of fit only 1.75. So meaning the lack of fit is not significant. So the low coefficients of variations and high R-square values, so indicated high precision and good reliability of the experimental value. And lastly, the ethical precision measures the signal to noise ratios, where a ratio greater than 4 is desirable. So this is another table that you encounter when you're doing the ISM CCT models. So this table shows the coefficients of regression models and their significance. So normally from here, we will analyze which factors, okay, will affect the response significantly. Okay, so for the p-value less than 0.05 is significance. Okay, the smaller the value, it will be more significance. And for the p-value larger than 0.05, it means this factor is insignificance. So then we move to this figure. So from these figures, it is noted that the predicted results from the responses fitted well with the experimental data. Okay, so just now from the data, you key in, remember the table, all right? You key in, then you compare with the predicted values from the software. So you will get this graph. So this graph shows your data is fitted well with the response because your point all here are distributed closely to the straight line. So this indicated that the derived quadratic polynomial models is applicable in optimizing the response within the investigated conditions. So the 2D contour plots shows the interactive effects, okay, between reaction time with catalyst loadings, all right, with your initial concentrations and with your solution pH. So what we get from these three figures here is the removal percentage increase with the longer exposure, duration to the UV irradiations. So mainly because of more photo-induced hole and the hydroxyl radicals will be generated. So which facilitates the degradation of the organic molecules. So another examples, okay, these 2D and 3D contour plots shows the interactive effects between the concentrations, okay, and the catalyst loading while keeping the solution pH constant. So the degradations percentage increase, okay, with increasing the catalyst dosage up to an optimum mass, okay, and then decrease with the excessive loading. So this is due to the availabilities of the sufficient active catalysts and no aggregation occurs for the zinc oxide particles. So at higher dosage and also at higher concentrations, the screening effects hinders the absorption of the photons on the catalyst surface, and therefore the degradation rate will reduce. So another 2D and 3D contour plots. Okay, so this contour plot shows the removal percentage increase as the pH and the amount of catalyst loaded up to an optimum value. Okay, so the decolorization efficiency, okay, was low at acidic pH. Okay, so because we are using zinc oxide, so there's a chance for the photocorrosions to occur. So the optimal removal was achieved when there is an electrostatic interactions between the anions of the dye. Okay, in this case is the EBT dye. All right. So and the positively charged zinc oxide surface. Okay, but you have to take notes that the hydroxyl radicals are rapidly scavenged at high pH due to the abundance of the hydroxyl ions, which inhibits the reaction with the dye's molecule. So therefore, when you are doing the photocatalytic studies, suitable pH should be carefully selected, okay, to ensure your photocatalytic degradations process perform the best. All right. So next, I want to share with you is the interactive effects between the concentrations and also the pH. All right. So we can see from here, the degradations efficiency reduce, okay, with increasing concentrations. Okay, as I mentioned earlier, this is due to the photon gap intercepted before they can reach to the catalyst surface. So one photon cannot reach, all right? So the active sites on the catalyst surface will inactivate, all right? So which reduce the PCO rate of the dye. So another possible reason is the Coulombic impulsions. All right, so between the negatively charged catalyst surface and the hydroxyl anions at a highly alkaline condition also reduce the removal rates by suppressing the generation of the hydroxyl radicals. So this is just the selected result from my previous research on how we're gonna analyze the 2Ds and the 3D contour plots and also the regressions plots from our experimental result and compare with the model. So after you done all of this, right? So of course you want to know whether your model is sufficient. Okay. So or in RSM the word is ethical. Okay. So in order to verify the model, so we need to run a few runs. Okay, we will carry out in accordance with the experimental conditions. Okay, of course, this condition also generated by the software, and then you need to compare with the predicted results. So if the experiment results were very close to the predictive values, so normally what they practice or what others people practice is less than 5%, but for me I will practice less than 3%. Okay, I want to make sure my model is really sufficient. All right, so then the developed model is reliable to optimize the photocatalytic process. All right, so I show you one of the examples. All right, so once you have set your conditions, okay, so you run it, then you compare with the software. Okay, so we calculate the percentage deviation here. So as I told you just now, if the percentage is less than 3, meaning your model is sufficient. All right, just a quick conclusions. All right, zinc oxide appears as an active and potential candidate for efficient photocatalytic degradations of various type of pollutants. So RSM is a promising as well as a powerful tool for multivariate optimizations of a photocatalytic process with systematic satisfactory results. So I would like to take this opportunity to thank MICNC 2021 Secretariat, okay, for inviting me to share my research experience. Also, of course, I would like to thank Nanotech who give me support during my research, and to my team members, okay, who always back up me when I face difficulties during my research. All right, that's all from me for today's sharing sections. Thank you for your time and hope to see you again, and stay safe.
Thank you. Thank you very much, Dr. Lee, for the great and interesting topic. So now we move to the questions. I guess we have one question in the chat box. It's from Dr. Chin. Well, presentation, Dr. Morris. What is the strength of zinc oxide as compared to other MOS photocatalysts such as titanium oxide, tungsten trioxide, copper oxide, and others?
Actually, as I mentioned just now, right? The zinc oxide actually has very high photocatalytic activities. Okay, as compared to of course, there are TiO2 and WO3 and copper oxide as well as mentioned by Dr. Lai. Okay, so but zinc oxide actually is appear as a suitable candidate. Okay, because one of the reason is it can operate as normal conditions. Okay, of course, the properties itself for zinc oxide can be tuned. So meaning we can modify the properties of the zinc oxide by doping or by doing the composite or supporting system as well.
Thank you, Dr. Lee. Another question in the Q&A. Thank you very much, Dr. Lee. Is it possible to incorporate zinc oxide into membrane for water purification purposes?
Yeah, it's possible, but because membrane, well, we need to as I say, there is a possibility we incorporate into it, but some parameters we need to carefully take notes, because as I say, the zinc oxide, although the property is very good, okay, but it needs to be modified and optimize the process parameters in order for both the zinc oxide or the membrane or the system that you need to apply later on to perform at its optimum peaks.
Thank you, Dr. Lee. Thank you very much for sharing us today.
Thank you.
Thanks. It was a pleasure for us to have you today with us. So now we have reached to the announcement of the session best presenter. So I'm very honored and pleased to announce that the Best Presenter Award for this session goes to Mr. Jonathan. Congratulations, Mr. Jonathan. And I would like also to thank all the speakers that have shared with us today in this session for their interesting topics and great sharing. So we have reached now to the end of this session. Thank you all for your participation. On behalf of MICNC 2021 Organizing Committee, I would like to seek your kind cooperation to fill up the feedback form as given by the moderators in the chat box. You are invited to join the rest of the event in networking expo. There's also the closing ceremony that will take place in the stage around 4 p.m., so half an hour from now. It was wonderful to have you all today, and I hope to see you again. Thank you, and congrats, Mr. Jonathan.